Hello, everybody.
Hi, Lennart here.
We're just finishing setting up here and should be ready soon.
I have a strong echo from you.
Okay, I will just say a few things. Okay. This is just a room audio test, sorry.
Okay.
Hi, Richard. Could you confirm that you hear me? That you can hear me?
Yes, Krishik, I can hear you well. Thank you.
Thank you.
Hello, everybody. We're going to start in less than 5 minutes now. Sound test. Sound test. So it's time for us to start. Yes. So welcome for the second day of our online conference, H0 2020, Assessing Uncertainties in Hubble's Constant Across the Universe. My name is Antoine Méran. I will be your chair today. We had an exciting start yesterday, I think, and our speakers discussed the accuracy of the distance ladder using Cepheids, tip of the red giant branch, type 1a supernovae, etc. They also discussed how H0 is derived from the cosmic microwave background, as well as what the quest for a concordance model means. We also had a lively discussion afterwards. We would like, as organizer, we'd like to thank all the speakers for the quality of their presentation, the panelists for their contribution to the discussion, and the participants, especially the one who asked questions. We would like also to acknowledge and thank the Scientific Organizing Committee for helping us to set up the program for this conference. By alphabetical order, we have Richard Anderson, who is the chair, Chuck Bennett, Annalisa Calamida, Matthew Colles, Frederic Courbin, Claudia Derham, Wolfgang Gieren, myself, Antoine Méran, as co-chair, Cho Chung Jo, Irania Peris, Michael Rigaud, Dan Skolnick, Sherry Suyu, our second co-chair, and Licia Verde. We'd like also to acknowledge the local organizing committee, Stella Cassiotis Klinger, who helped us set up the conference. So today we will dive into the heart of the Hubble tension by looking at stellar distance indicators. First, we'll look at the role of the Gaia astrometric mission. Then we look at stellar candles. Then the promising role of Mira stars. And finally, a review on type 1a supernovae. The talks are being recorded. So if you're just joining us and you missed yesterday's talks, it's already on YouTube and you can check the recordings. You will find the link on the program webpage of the conference. Now I would like to make a few reminders about how this online conference is organized. So like yesterday, we'll have 4 presentations today. If you want to ask questions to the speakers, we use a service called Slido to collect your inputs. So to access the service and to ask questions, go to the program's webpage, which is shown right now, and you will see a link called Q&A, and it just write on each talk. So each talk has its own Slido page. On this page, you can ask a question at the top, and we will ask you kindly to provide your name so we can ask the question in your name, but you can also upvote the question. So this is, for example, from yesterday's, and you can see that we had the top question here, the remaining question was there. After the talk, of course, we will ask the question. But after we answer all the questions, the speakers answer the question, you can continue asking questions and upvoting them, because we might use them as well for the discussion session. So the last pillar of our conference is Slack. So where registered users can interact with the speakers, other attendees, and the organizers. If you register to the conference, you should have received a link to join us in Slack. If you have not received this email, please inform us at h0@eso.org, send us an email, and we will send you back the invitation. Slack is the place for follow-up discussions, and we encourage the speakers to address the unanswered questions there. Some questions have been answered already in the Slack from yesterday's talk. We also have a Twitter handle, #H02020. So if you'd like to join the discussion and let other people know what is happening, you're welcome to do so. So I would like to invite you all now to turn on your camera, and we can all say hello to every of us for a few moments. A lot of people. So thank you. So I would like now that people, you mute yourself and turn off your microphones, so we can soon start the first talk. We still have a few minutes, I think, so we can use these minutes, I think, to ask the first speaker, Lennart Lindegren, who I see is already ready to go. So Leonard, if you can share your screen already. Yeah, so just use the Slido. You should ask your question earlier and not wait for the end of the session to start asking your question, because there's this thing when you can upvote questions. So if you have the opportunity to ask a question earlier, your colleagues might be able to upvote your question and your question may be asked. Whereas if you ask your question at the last moment, you won't get so many upvotes. So please try to upvote, to post your question early. So I think we have a lot of participants already logged in, so we should start the first talk, I guess. So the first talk will be given by Leonard Lindegren from the Lund Observatory. He's going to talk to us about Gaia astrometry and this contribution to the distance scale. So Leonard, please go ahead.
Thank you. I suppose you see my screen then and can hear me?
Yes, we do. We hear you and we see your screen, so you can go ahead.
Thank you. So I will start by giving a brief overview of the Gaia mission for those who are not familiar with it. It is a survey aimed to collect astrometric and spectrophotometric data for more than 1 billion objects, and also radial velocities for more than 100 million sources. It's a survey with autonomous onboard detection of point sources at a resolution of about 1/10 of an arcsecond. And it will, in this way, detect and observe practically all objects between magnitude 6 and 20.7 in the wideband optical system defining the G magnitudes, defined by the sensitivity of the CCDs. So the science objectives range from the solar system to cosmology, with an emphasis on stellar astrophysics and the structure and formation of the galaxy. The Gaia satellite was launched by the European Space Agency in December 2013. It is currently in an orbit around the second Lagrange point, L2, 1.5 million kilometers from the Earth. It has a nominal lifetime of 5 years, which have already passed. We are well into the 6th year of operation. And the technical lifetime is up to 10 years. It observes in a scanning mode, which gives full sky coverage in half a year. And then this scanning is repeated over and over again, so that each part of the sky is visited on average 14 times per year, with multiple observations each time. This gives a quasi-irregular time sampling, which is actually very good, not only for the astrometric measurements, but also to detect variable objects and analyze them, variable stars, for example. As a very specific feature with this instrument is that it has 2 telescopes set at a fixed angle, the so-called basic angle of about 106 degrees to each other. And this gives the capability of accurately measuring large angles on the sky, which is fundamental for the measurement of parallaxes, among other things. So the primary data products are of 3 kinds. There is the astrometry, the low dispersion spectrophotometry, and the high dispersion spectrophotometry with radial velocities. So the astrometry is generated by the central part of the focal plane, which is occupied by 62 CCDs. And the detected point source is a small window around each such source is read out and sent down to the ground for analysis. And what is done there is essentially that the line spread function or point spread function is fitted to the currents. And this gives the position of the object relative to the CCD and also the flux. And from this eventually is derived the astrometric and G magnitude. There is also 2 photometers called the BP and RP, blue photometer and red photometer, which have dispersive elements in front of them, so that we have very low resolution spectra that look like these here. And from these are derived integrated photometry, which is the total flux in these two wide bands, and low dispersion spectra like the ones shown here. And finally, there is the radial velocity spectrometer, which observes a small section of the spectrum in the near infrared containing the calcium triplet. And this is mainly used for determination of radial velocities, but for the brighter sources, the spectra also contains a lot of useful astrophysical information. So based on these three different kinds of data, a lot of additional information is derived. For example, time series of the photometric and astrometric variations, object classification and analysis, especially concerning binaries and multiple stars, and also astrophysical parameters by combining, for example, parallaxes and spectrophotometry. So the latest release was the second data release more than 2 years ago in April 2018. This gave astrometry and integrated photometry for 1.3 billion sources and radial velocities for 7 million sources. The next release is what is called the early third data release, which will come late this year. It will contain improved astrometry and integrated photometry for, I think, about 1.7 billion sources. The full third data release will come about a year later. It will contain a deeper radial velocity survey than in DR2, the complete BPRP and RVS spectra, and information about non-single stars, extended objects, and so on. A very interesting part of this release, I think, will be the so-called Gaia Andromeda photometric survey, which is the complete photometric time series for all sources in a pencil beam of 5.5 degree radius centered on the Andromeda galaxy. The next release, again, the fourth release, will be based on the data from the full nominal mission and half a year into the extended mission. So the data for that has already been collected, but are not yet analyzed. And since we are into the extended mission and hope that the mission will last a number of years yet, there will be a fifth release at some time using all the data that the satellite collects. So looking into the Gaia astrometry, the first two releases treated all sources as single point sources, including AGNs and other extragalactic objects. This means that they can be astrometrically described by 5 parameters per source, which are 2 components of the position, the trigonometric parallax, and the 2 components of proper motion. For the bright sources, we also have the radial velocity, which means 6 parameters, which completely give the phase space coordinates, that is the position and space velocity of the star. This is actually a good approximation for about 80% of the sources, even though many of them are not single sources, single stars in reality. All of these results are derived from differential observations in the focal plane of Gaia, that is with a single instrument, so that the data are in principle on the same system. So for example, the positions are linked to the International Celestial Reference System using about 3,000 quasars that have accurate positions determined from decades of radio interferometric observations. The proper motions are non-rotating, in a non-rotating system, thanks to about 500,000 of quasars, where the astrometric solution is made in such a way that on average, these quasars have 0 proper motion. And finally, the parallaxes are absolute thanks to the wide-angle measurements, which I mentioned before. This is how it works in principle. In reality, of course, there are systematic errors caused by imperfect calibrations of the instrument and also the need to span a huge range in magnitude, about 15 magnitudes, which corresponds to a ratio 1 million in flux. And it's very difficult to get the instrument to operate in exactly the same way for the brightest sources and the faintest ones. But that is what we have to achieve by means of the complex calibration model. So a useful model for the errors in the astrometry, take for example the parallaxes of sources in data release 2, is to describe the difference between the parallax as given in the catalog with a true parallax as consisting of two components. One is the random errors, which are truly independent for the different sources, and roughly follows a Gaussian distribution with standard deviation equal to the formal errors given in the catalog. But then there are the systematic errors, which may depend on a number of variables, like the position of the star, the magnitude, color, and so on, possibly many other parameters which we don't even know about. And the characteristic thing about what we call here systematic errors is that if you have two sources that are on roughly the same position in the sky, have roughly the same magnitude and color and so on, they will have the same systematic errors, even though their random errors are different. So when we talk about the parallax 0 point for Gaia data, we actually mean this systematic error here. And it should be clear then that there is not just one parallax 0 point for Gaia. It is a complicated function of a number of variables. And it would, of course, be very nice if we could calibrate this and say that if you have a star of this position, magnitude, and so on, then you should add this correction to the parallax to get a better unbiased value. But that will not be possible. There is, however, one group of objects for which you can do a limited mapping of the systematic errors, and that is the quasars, because we know that the quasars have negligible parallax and negligible proportions. So if we make a map, for example, of the quasar parallaxes, as shown here, and smooth it with a Gaussian beam so that we remove most of the random errors, what we are left with is a map of the systematic errors versus position for the quasars, which means that it's averaged over the magnitude and color distribution of the quasars and so on. And you can see that, well, there is this white band here, which is the galactic plane, because there are simply too few quasars here to compute reliable averages. So that is blocked out here. But in the rest of the sky, you can see that most of it is bluish, which means that the mean parallax of these quasars is a bit negative. And in the mean or median, the parallax of these quasars is minus 29 microarcseconds. If you take these smoothed values and compute an RMS value of the smoothed values, the RMS in this case is 20 microarcsecond. It will be different depending on the size of the beam you're using. The larger beam will give smaller RMS values. And this gives a characterization of the typical level of the systematic errors as a function of position at this magnitude. But if you then plot the quasar parallaxes versus magnitude instead, this is what you get. The yellow points are the individual parallaxes, so they have a huge spread here in this diagram because the scale is blown up very much here. But you can see that most of the quasars have magnitudes from 18 to 20, and there the mean parallax is about minus 30 microarcseconds. But if you go to the relatively few quasars that are much brighter than this, down to 15, 14 magnitude, you can see that the average parallax then is more like minus 50 microarcseconds. So there is a magnitude dependent variation of this systematic or parallax 0 point if you want. Similarly, if you plot the quasar parallaxes versus color, in this case, the color index BP minus RP, which is very close to V minus I. Most of the quasars have relatively blue colors, and the mean parallax is again minus 30 microarc seconds. But if you go to the much redder quasars, the 0 point is again more negative. And perhaps also if you go to the very bluest quasars. There is a strong correlation between the colors and magnitudes of the quasars. So these dependencies are not so easy to separate. Since the second data release 2 years ago, a number of studies have been published where part of the study has been an investigation of the parallax 0 point in DR2. And I'm listing here a selection of these studies from the original publication that went with the release, where the 0 point was said to be minus 29 microarc seconds. This was based on the quasars that are typically at 19th magnitude. But most other researchers have found more negative 0 points. But they have also used a variety of different methods, and typically they use much brighter objects. And I think the main reason why they get more negative 0 points is that these objects, Cepheids and so on, are much brighter than the quasars. Now, looking into the future, as I said, the nominal mission started in mid-2014, and we are already past the nominal mission, which was 5 years, and has almost gone 1 year into the extended mission. So far, Gaia has collected more than 1.5 trillion astrometric CCD observations of the kind which I described before. And we hope that Gaia will continue to observe in this way until the end of the technical lifetime, which would be sometimes in 2024. An important thing to note is that the second data release, which is what people have been working with so far, is only based on the first 2 years of the mission. And even the early data release 3, which will come late this year, is only based on the first 3 years. So in the next releases, data release 4 and 5, with a bit of luck, and if Gaia continues to work to the end of its lifetime, we could double this amount of data twice. Looking now at the random errors, and we start with the parallaxes. These are plots of the parallax uncertainties in data release 2 and early data release 3 as a function of magnitude. And the white line here is the median. And you can see that there is a clear improvement, especially for the bright sources. And at magnitude 15, for example, the improvement is a factor 0.7, roughly. This is what is to be expected because there is roughly twice as much data used in DR3 than in DR2. So we get this improvement by the square root of the number of observations. If we go to the proper motions, the improvement is even better because there we also have a longer time baseline from which the proper motions are determined. And the black lines here, I forgot to mention that on the previous slide, they are extrapolations of the median accuracy that can be expected after the 5-year mission, that is DR4, and the 10-year mission, which is the best we can hope for in DR5. So these are the random errors. If we look at the systematic errors, I showed smooth maps of the parallaxes before, quasar parallaxes. Here are quasar parallaxes and proper motions of the quasars, and in DR2 in the upper row and in DR3 in the lower. And you can see that also the systematics improve with factors that are at least as good as the random errors. So at least from data release 2 to 3, the systematic seem to improve faster than the random errors, which is good, of course, but also expected because as we get more data, we also learn to understand the instrument much better. And this will hopefully continue in subsequent releases also. Coming now to the contributions of Gaia to the distance scale, the most important part is, of course, the trigonometric distances. And I would especially like to point out this table here, which gives the number of sources that have trigonometric parallaxes to better than 10% and 1%. So in DR2, it was 2 million. In DR3, it will be 5 million better than 1%. And in the future releases, this may again be much increased. So this will, I think, determine a geometric distance to the Magellanic Clouds just from the parallaxes. It will resolve the depth structure in the clouds. But it will also be possible to determine rotational parallaxes for the large Magellanic Clouds by combining proformations and radial velocities. And this will even be possible for the two nearest big spiral galaxies, M31 and M33, where the amplitude of the proformations are 70 and 25 microarcseconds per year. And many sources will be observed in these galaxies. But I think perhaps in the long run, most important contribution to the distance scale will be the general cleaning up of our knowledge and understanding of the local universe, and especially the synergy between observations and theory that will allow us to get much better fundamental stellar parameters and also understand stellar multiplicity better. And we will have a three-dimensional extinction map from Gaia, for example. And all of this will provide, I think, a very solid basis for the next steps in the distance ladder. Thank you.
Okay. Leonard, can I ask you to conclude, or was it your conclusion already?
That was my conclusion. Thank you.
Excellent, just in time. So thank you for this overview of the Gaia mission and the upcoming DR3. I think everybody is excited, as we can tell in the questions. So the top questions right now is, can we expect improved characterization of the 0-point offset in early DR3 release? And it was asked by Adam Rees.
Yes, I think we can do that because we have not only improved statistics, but also we are now very conscious of this problem and will do whatever we can to characterize the 0-point.
Okay, and the second question by Richard Anderson here at ESO is, what is your take on 0-point offsets for objects with time-dependent color, such as pulsating stars? What is the plan to include this in the astrometry?
In DR3, there will not be any attempt to do that. The problem is that already when you do the LSF fit of the original count, you have to choose the LFS for the appropriate color. And that is not done yet, but it will be done in data release 4. So there we will use the, if the object has a variable color, we will use the color relevant for that observation. And that should eliminate that kind of error source, I hope.
Thank you. And I think we have time for at least one more question that I asked myself is, in the systematics map on the slide 8, what causes the yellow patches of positive parallax biases, whereas most of the map is negative?
Well, it is just part of the random fluctuation. I mean, it's more or less a Gaussian fluctuation around -29, which just is strongly correlated across the sky. With a typical correlation length of a few tenths of degrees. And that is what is seen here. So it is accidental that it is in that part of the sky.
Okay, so I suggest we answer the last question before moving on to the next talk. And this was asked again by Richard Anderson. And he asked, The 0 point of red quasars matches that of similarly colored Cepheids, approximately 48 micro arc seconds, even though they are brighter. Does color or magnitude dominate the 0 point?
That's a tricky question because for the quasars there is a strong correlation between magnitude and color. So I don't think I can answer that really. But I think the magnitude effect is probably the stronger one, I would suspect. We will know that kind of detail much better in the coming early data release 3, I think.
Okay. Well, thank you for making us even more excited by the early data release 3. And thank you for people who ask questions. And I think we can move to the next speaker, Grzegorz Petryński, who is going to talk about the absolute distances to standard candles. Grzegorz, if you're ready, please unmute yourself and go ahead.
Okay, I'm ready. I will share my screen in a moment. Where is it? Okay, I hope you can hear me well and see my slides.
So for now, we can see Slack. We cannot see your slides.
Okay, I will try to do it again. How about? Okay.
Share the app, not the, okay, now it works.
Okay, can you see the slides right now?
We can hear you, we can see your slides. Please go
Excellent.
ahead.
Okay, I would like to thank the organizers for big efforts to make this meeting possible. It's a pleasure to attend it. Well, and I would like to thank for the opportunity to present some results obtained in our long-term Gaia project. We started it about 20 years ago, and but the main goal remains the same. We try to improve the cosmic distance scale calibration based on observations of several primary distance indicators in nearby galaxies. We have been observing Cepheids, blue supergiants, red club stars, RLR stars, tip of giant branch magnitude, and eclipsing binaries. So far we have published about 150 papers, and today I will concentrate mostly on eclipsing binaries. Well, to calibrate Supernova 1A, we need to do two crucial steps. First of all, we need to calibrate the 0 point using geometrical methods. And then we need to bridge these geometrical distances with supernova. And for that, we need we need to use standard kinds like Cepheids, tip of a giant branch, or others. So we have two possibilities to calibrate these techniques. First, we can use individual distances obtained with Gaia, HST, or Brother-Wesseling method. We have heard about fantastic possibilities regarding Gaia. And another possibility is to measure a geometrical distance to nearby to a given galaxy, like LMC, which hosts a rich population of different distance indicators. And using that, we can calibrate different techniques. Well, doing it, we need to take care about several very important problems like population effects, extinction, calibrating the 0 point, correction for blending and crowding, and of course we should know the basic physics behind the distance indicators. I will try to convince you that with eclipsing binaries we can take care of all these problems very well. Because in the case of eclipsing binaries, we can measure distances using this simple equation. Based on analysis of the light curve and radial velocity curve, we know how to calculate dimension of stars with a precision better than 1%. And we know how to do that. We have known how to do that already in the 90s. Right now, with data from satellites like Kepler and TESS, we can do it even much more precisely. Well, if we adopt surface brightness curve relationship, which is very well established for late type stars based on interferometric observations, we can also obtain angular diameter. And having both, we can calculate distance very easily. So until 2019, the scatter on the relationship between surface brightness and color was about 0.03 magnitude, which means 2% in angular diameter determination. But the problem was that the main problem was that to calculate distances to nearby galaxies was related to the fact that we didn't have eclipse invariance composed of late type stars. Such stars are quite faint, and on the main sequence they would be too faint to observe them in nearby galaxies. Fortunately, thanks to the effort of several microgalaxy cover teams, mostly by all collaboration, we were able to select a few dozens of eclipse invariants composed of late type giants, and such systems are perfect for distance determination. Here you can see an example of the data. It took us about 20 years to come up with spectroscopic and near-infrared data, and together with photometric light curves, we were able to analyze them and measure distance to the large and small Magellanic Cloud. In 2019, we improved the calibration of the surface brightness curve relationship. Right now, the RMS scatter on this relationship amounts to 0.018 magnitude, which means 0.8% in angular diameter determination. Well, then we applied this new calibration to measure distances to 20 systems in the Large Magellanic Cloud. Individual distances were accurate to about 2%, but these individual distances were dominated, these errors were dominated by statistical errors. Of course, if we had better data, we would be able to get better precision, but that would be quite expensive from the point of view of the telescope time. But it's just enough to have such a precision for the time being. Let's take a look at the systematics. Well, one of the major problem when calculating distances is the reddening. In this case, we have a very fortunate situation. If you take a look at this diagram, which presents surface brightness curve relationship for different colors, in the lower panel we have calibration relationship for the V minus K color, and the reddening line is marked with an error. As you can see, the reddening line is parallel to the relationship. And this is how we calculate angular diameters. This is the definition of the surface brightness. As you can see, the reddening should affect surface brightness and observed magnitude in the same way. So this effect should cancel out. And this is why the dependence on the reddening is so small. It amounts to 0.4%. If we change the reddening law very significantly by 1, that would result in a change of the distance of about 0.2%. So this technique is pretty insensitive to the reddening. Metallicity, well, some time ago we calculated an upper limit of dependence on the metallicity to be of about 0.2%. Well, again, in this figure, you can see how surface brightness depends on the metallicity. I plotted here two synthetic relationships, one for solar metallicity and the other one for metallicity equals to -2. So we have 2 decks of difference, a huge difference. And in the case of the relationship between surface brightness and V minus K color, it's hardly to see, in this scale at least, any difference. But in a recent paper, Jeremy Mould suggested that this effect can be larger. But actually, we can check it empirically. In this plot, you can see O minus C from the fit of the surface brightness curve relationship for our calibrating system in the solar neighborhood. As you can see, we have a quite large range of metallicities, almost 1 dex. And well, as you can see, there is no dependence on metallicity at all. the coefficient of determination equals to 0.0001, which means that there is no relationship. This is the range of metallicities of our systems in the Large Magellanic Cloud. As you can see, we shouldn't expect any shift, but we can play a little bit. We can select all the stars in this range of metallicities, for example, in the solar neighborhood and in the Large Magellanic Cloud. We can calculate distance, and the result is virtually the same as we obtained from the whole sample. So the final distance determination, we combined. We need to combine individual determinations. We can take simple mean, correct for geometry, adopting one of the existing models. But having 20 precision distance determinations, we can also obtain our own geometrical model. We did it. As you can see, in all cases, the mean distance is basically the same, which means that the geometrical extension of the Large Magellanic Cloud should not affect our mean magnitude in a significant way. Systematic errors amounts to 0.026 magnitude, and it includes surface brightness correlationship, uncertainty of photometric 0 points, and reddening. We published this result last year. What is very important, we can use also binaries to obtain independent distances. If our binary systems are located close enough to resolve them using interferometric techniques, for example, we can measure distance in other way. From the feet of the spectroscopic orbit, we can obtain linear. We can determine the dimension of the semi-major axis in absolute units, and from interferometric orbit we can measure the projection of the semi-major axis on the sky. So we can infer distance immediately, and this can be done with a precision close to 0.5%. As you can see from excellent work done mostly by Alex Galen, Antoine Morel, and Pierre Crivella. And we can achieve such unprecedented accuracy for such systems. So we selected 12 systems for which we can apply our eclipsing binary method plus surface brightness correlationship, and we can resolve them interferometrically to apply the other technique. Here you can see the results for one of them from TZ Phonaxis. Spectroscopic orbit is based on HARPS observations, so it's extremely precise. And the astrometric orbit is from VLTI observations with Pioneer, which is also extraordinary precisely. So for this object, we obtained measured distance using these two methods, and as you can see, the agreement is just perfect. It's too early to compare our results with Gaia parallaxes because the apparent orbital motion is unmodulated for the time being. But in the future, we will do a comparison between our completely independent distances and Gaia parallaxes, which is very important because, as I mentioned at the beginning, our main goal is to calibrate Supernova 1A. We need to use intermediate step like C-phase, the preferred giant branch, or whatever else. And we have three geometrical techniques to choose from: eclipsing binaries. And the big advantage of this method is that we can apply it already now in the volume of 1 megaparsec. In the future, with extremely large telescopes, we can increase this range even more. Gaia will provide beautiful parallaxes in the Milky Way, and astrometric binaries are very helpful to check for possible systematics in these two methods. So in the Large Magellanic Cloud, we could use, we have a rich population of different distance indicators. This is a wonderful laboratory to study different processes, and in particular to calibrate different standard candles. In this plot, in the upper plot, you can see period to velocity relations, which are clearly the best for the time being. And together with our geometrical distance, we can calibrate C-phase, tip of a giant branch magnitude, and other techniques in the Large Magellanic Cloud. In the lower panel, you can see very precise calibration of the period investigation for C-fates, for the Milky Way C-fates. The result was really highlighted by Adam. It was obtained by Luis Breval and collaborators. And from this, we have already a taste what is possible to achieve based on Gaia. So we will have two independent, very precise 0 points in the future. But in order to use these geometrical techniques to calibrate standard candles, we need to correct them for reddening. And in the case of LMC, it's easier than in our Milky Way. But it's not trivial, of course. Well, in order to come up with reddening corrections, we constrained reddening maps. We published them in 2020. We used V-I color of the red clump stars as reddening tracer. And as the 0 point, we choose empirical determinations of reddening based on our eclipsing binaries. So we have 20 individual determinations. And the age of our systems are between 200 megayears and 1 gigayear. We also used 33 determinations based on blue supergiants, very young massive stars. And 0 point of our maps is accurate to about 0.013 magnitude. And the mean EB minus V reddening amounts to 0.0127 magnitude. Well, we compared our reddening maps against individual determinations, very different determinations. While there are some solid reddening determinations for other type of eclipsing binaries, like HV 2274, for example, also for clusters and tip of a giant branch magnitude obtained recently by Freeman et al. As you can see, in all the cases we have a just perfect agreement, which reinforce our approach. We can also compare our reddening maps with corresponding maps obtained with other reddening tracers like C-fates, RLR stars, and also different approach with red clump stars. So if we compare, for example, our reddening maps with the maps obtained based on C-fates by Ina et al., this is beautiful work done in 2016. The mean difference amounts to 0.004 magnitude. Between our maps and Peja and Stanek, we have a difference of minus 0.022 magnitudes. Well, Choi et al. Calculated reddening maps based on slow bands of red clump stars, and again we have a beautiful agreement. Well, there is another attempt to obtain reddening maps based on colors of the red clump stars, and adopting the 0 point from the Schlegel maps in the outskirts of the Large Magellanic Cloud. In this case, the difference is slightly larger, there is also there are some papers adopting theoretical corrections for the red color of the red clump stars, Heshte et al. And recently Nataf et al. And in this case, we have a much larger, huge difference, which is 5 sigma tension. Just to conclude our efforts to correct for reddening in the Large Magellanic Cloud in the Milky Way will be even more difficult to do that. Blue supergiants might give us a bit larger reddening, but anyway, if we adopt reddening from eclipsing binaries, we use 3 different methods to do that. And blue supergiants, anyway, we have a very good agreement. If we exclude blue supergiants, we have a slightly better agreement with other reddening maps. We have very consistent results from different tracers like red clump stars, tip of a giant branch magnitude, RLR stars, and C-fates. If we include theoretical colors, corrections from theoretical models, which are quite uncertain because models depends on many different parameters, we have 5 sigma difference. But let's assume for a moment that this is correct and all the empirical determinations are wrong. This would have very strong consequences. First of all, our distance determination or eclipsing binaries should not be used in such a case because it's not consistent. And if we would like to adopt this reddening 0 point to calculate distances with eclipsing binaries, we would have very serious problems. First of all, the colors of our reddening components of the eclipsing binaries would be redder by about 0.13 magnitudes, which is a huge difference, which means 200 kelvins difference in effective temperature. And well, it would be very difficult to obtain consistent models for our eclipsing binaries, so we can exclude such a big difference. And the other consequence is that if we go to the R case of the Large Magellanic Cloud, we would have very low reddenings, which is not the case because we have foreground reddening, which equals to 0.06 magnitude roughly. We can calculate it from maps of Schlegel. So just to make a short summary, well, with eclipsing binaries, we can provide independent 0 point determination of the whole extragalactic distance scale. We can provide distance to the large, we provided already distance to the Large Magellanic Cloud with a precision of 1.2%. We can improve on that in the near future. For the Small Magellanic Cloud, we will publish 2% distance determination this year. Other galaxies, well, it's quite difficult to find such eclipsing binaries, but we can use early type systems and well, achieve a little bit lower precision. Well, this is crucial for calibration of major distance indicators because we can provide not only the calibration of the 0 point, but also check on the metallicity effect. Reddening in the Large Magellanic Cloud can be obtained very precisely. And in order to be able to calculate, to obtain Hubble constant accurate to 1% or 2%, which is it's imperative to use more than one technique. So hopefully with Gaia and eclipsing binaries, we can do that in the future. Finally, I would like to say that it has been an honor and privilege to collaborate with so many excellent astronomers. In particular, I would like to highlight the input from Darren Gacek, Ian Thompson, Alex Galen, and Wolfgang Gieren. Thank you very much for your attention.
Thank you, Gregor, for this very detailed explanation how you measure distance to the Magellanic Clouds. We have many questions, so I will start right away by a question by Pierre Carvela, who asked, to mitigate the effect of metallicity and reddening, infrared K-band photometry is very valuable. Eclipsing binary cepheids, what are the prospects to collect new data?
Well, in the Large Magellanic Cloud, I would say we have quite a lot of different infrared data from different sources. There is a VMC survey from ESO survey, for example, but it's quite difficult to collect precision infrared photometry for bright systems in our galaxy. So this is a challenge, and we need small telescopes to do that, to be able to do that. And it can be a problem in the near future. So there are some perspectives, and for example, we are trying to assemble a small observatory in ESO to collect precision infrared photometry for very bright systems. But for Magellanic Clouds, I believe that we have enough good infrared photometry. Well, of course, it would be nicer to have, for example, complete light course or eclipsing binaries, but that would be very difficult.
We have another question by Anupam. Is it possible to get a 1% distance to the Small Magellanic Cloud, regardless of its complex structure?
I would say it's possible to obtain a 1% distance to a given binary system if we have, very good data. But a mean distance to the Small Magellanic Cloud, we can forget about it, precisely 1%, because the geometry of this galaxy is very complicated. So individual distances, yes, but the problem will be how to combine them and how to calibrate other standard candles based on our distance determination. We can provide 1% distance, but the question is to what point,
I see. So the next question is from Richard Anderson, who says that Guérin et al. In 2018 find that a long metallicity lever, that means, for example, SMC versus Milky Way, is required to see a metallicity effect on Cepheids. Could the same be true for the surface brightness relations?
For the Cepheids, or for the surface brightness correlate relationship, I wouldn't expect a big difference, a big influence from metallicity. As I showed the synthetic plots from both theory and from empirical data. So I wouldn't expect strong dependence on metallicity.
Okay, so we have maybe time for 1 or 2 more questions. The next one is an anonymous question and asks, how do you know the physical radius measured by the light, I suppose the light curve, and radial velocity on the one hand, and the angular radius from SBC relations are measuring the exact same surface of the star? I guess because it can produce a bias in your distance estimate.
I don't. Well, the principle is, well, in principle is very simple, because we just analyze the light curve or the velocity curve. You know, for the light curve gives us information about that. This is geometrical effect. So we can measure analyzing the light curve, and basically the limit comes from the quality of the light curve. We can infer the size of the star in units of the semi-major axis. So in other words, it's radius divided by semi-major axis. And from the radial velocity curve, we can infer semi-major axis in in absolute units, in kilometers. The first determination 100 years ago was in miles, for example. So combining two, having both light curve and radial velocity curve, we can infer immediately absolute dimensions of eclipsing binaries, of the component of eclipsing binaries. So this is very well known, and we know how to deal with that. And we don't push for you know, the method, because as I showed you, 1% is very easy to achieve with modeling eclipsing binaries. We can obtain much better, much more precise determinations.
Okay, I think it's time to move to the next speaker, and thank you, Gregor, again for your nice presentation, and thank you for people who ask the questions. So our next speaker is Caroline Wang. I don't know if she's here, and she can share her screen.
Hi.
Hey, hello.
Okay.
So you're going to talk about Mira distance ladder.
Yeah, that's right. So my name is Caroline. I have been working on the Mira distance ladder, and my collaborators are Adam Rees, whom you've heard talk on Monday, Wenlong Yuang, Patricia Whitelock, Nadia Zakomska, Stefano Casertano, who'll be talking on Friday, and Lucas Macri. And I'll just be going over some of our recent work and a little bit of future prospects. So first, just an introduction again into the Hubble tension, which is that early universe measurements of the Hubble constant, which infer the Hubble constant from early universe physics, consistently obtain a lower value than late universe measurements of the Hubble constant using direct distance ladders. And so now that we have multiple independent direct measurements of the Hubble constant in the late universe, these can also be added together to give us an even larger tension between the early and late universe. And as the precision of these measurements has increased, the tension has also grown. So it's now something that we're very concerned about. And today I'll be focusing on the work using Miras in measuring the Hubble constant. So as the previous talks discussed, this is the Cepheid supernova distance ladder. And the Cepheid supernova distance ladder, geometric measurements to Cepheids nearby are used to calibrate their luminosity. And then the luminosity—
We don't see your slides changing. We only see the title slide.
Oh, I'm sorry. let's see. Okay, let me try this again. Okay. Can you see the change this time?
Yes, we do.
Okay, sorry. So earlier when I was discussing the Hubble tension, I meant to show you this plot. And this is the work I'm going to be talking about. So this is the Cepheid supernova distance ladder. And the first rung of the distance ladder is using geometry to get the distances to Cepheids nearby and their luminosities. And then these Cepheids are used to get the luminosities of nearby type 1a supernovae. And then these type 1a supernovae luminosities can directly calibrate the type 1a supernovae in the Hubble flow, which measure the Hubble constant. So one reason why we're interested in looking at Miras is that Cepheids are young, massive stars, and they're only used to measure distances to type 1a supernovae in galaxies with recent star formation. So Miras, the ones that I will discuss, are an older and less massive population, and thus we can use them to measure distances to type 1a supernovae, even in elliptical or S0 galaxies. And in fact, one of the panelists speaking later today, Marina Rekuba, actually did this to Sen A. And that was, I think, before this work, the farthest Miras that had ever been seen and measured. And so I also wanted to point out that this is actually a really impressive measurement in which there's 4 different anchors that span 23 magnitudes with less than 2% error in the Cepheid distance ladder. So Miras are not at that point yet, but we're hoping to have an equivalent distance ladder with Miras instead of Cepheids. And so what is a Mira? Well, this is the HR diagram, and Miras live on the asymptotic giant branch. They're in fact some of the most bright stars in the asymptotic giant branch, so they live near the tip, and they have a periodic variability. And their periods are also correlated with their luminosities, similarly to Cepheids. So it's physically motivated because they're fundamental pulsators. And Miras are also extended objects. So here is a picture of Mira that was actually taken with Hubble Space Telescope, and you can see that we can resolve them. This becomes important because it makes their parallax measurements inaccurate. And they also have very large amplitudes of variability. In fact, the largest out of all pulsating variables. So in the lower left is the light curve of Omicron Ceti, which is the same Mira that's on the right. It's the one after which all the others in the class are named. And it has a period of about 330 days. This data was actually taken by amateur astronomers. You can see that the amplitudes of variation are several magnitudes in visual wavelengths. And you can also see that there's a little bit of a variation in the amplitude between cycle to cycle. However, the period remains consistent. This amplitude of variation actually is much smaller in the near infrared, and the differences in the amplitudes between different periods are also much more consistent in the near infrared. So we primarily look at Miras for the distance ladder in the near infrared because that is where they follow their period luminosity relations. And as I mentioned earlier, they have the largest amplitude of periodic variable stars. So on the left, you can see this plot of H-band amplitude for LMC variables for the Cepheids, type 2 Cepheids, and Miras. And this circle down here is the SRVs, which are low amplitude, long period variables. But for the distance ladder, we'll primarily focus on Miras with periods of less than 400 days. The other thing I want to draw your attention to is the fact that there's 2 spectral classes for Miras, carbon-rich and oxygen-rich, and they follow slightly different PL relations, as we can see in the lower right. So this is the K-band PL relations of Cepheids and Miras, and the Miras are in black and gray. And we can see that the O-rich Miras follow this clean PL in the K-band, but the C-rich Miras have more of a clump. So it's important for us to separate the O and C-rich Miras in order to obtain a clean PL. In addition, the Miras are also brighter than Cepheids at K-band, and they're comparable in H-band, where we focus our HST observations. So while being similar in luminosity, they have 2 advantages over Cepheids, being ubiquitous and detectable in the near infrared. Cepheids in the near infrared have low amplitude variations, and thus they're typically detected in the optical and followed up with near infrared data. So the Mira distance ladder has two anchors. One is the LMC, and the geometric distance, as we just heard, has been measured to great precision as of 2019, and it's precise to 1%. And so on the right here is the LMC, and it was observed extensively by Ogle. And Ogle discovered many Miras and SRVs in this galaxy. So you can see these points are evenly. So this is a plot of Miras in red and SRVs in blue from the Ogle website. And you can see that they're both pretty much uniformly distributed across the galaxy, which is a sign of them being an older population. And in the bottom here are the three Mira PL relations from Yuan et al. 2017 in J, H, and K. And they used a quadratic fit to the PL relation. And the oxygen-rich Miras are in blue and the carbon-rich Miras are in red. So the other anchor is 4258. So 4258 is host to a water megamaser galaxy, and we'll hear more about maser distances later this week. But this also has a distance, a geometric distance with a 1.5 precision. And we observed NGC 4258 in 12 epochs using near infrared F160 and F125 data from HST. And we were able to discover Miras and obtain light curves for them. So what I'm showing on the upper right here is the light curve of a Mira that we discovered in 4258. It's not one of the ones we included in our final PL relation, but I've used it here because it has a large amplitude, and you can actually see from each of the individual stamps how it's getting brighter and fainter over the course of our observations, corresponding with the points in the light curve. So, and then these are the PL relations for our overall sample detected in 4258. So in 4258, we also had previous Cepheid searches, and we were able to plot up the Cepheids from the previous search. And you can see that on the left, they follow this star-forming regions in the galaxy because they're young massive stars. And on the right, where we search for Miras, also in blue, these white boxes are the WIFC3 footprint. We can see that they have a uniform distribution, as we would expect from their older population. Another thing that we were able to do, because we had both of these sets of data, is to confirm that no Cepheids were falsely detected or aliased as Miras. So in 4258, we also had the benefit of, due to the Cepheid search, some optical data in which we tried to use to derive sample selection criteria, because this was the first galaxy that we'd ever observed with Miras using HST. So we created 3 grades of Mira samples based off of how much optical confirmation of their periods and their variability there was. And we actually found that these 3 grades, with gold being the most strict and bronze using only near infrared data, produced 0 points that were consistent with each other to within their errors. So this was a good sign to us because it indicated that optical data was not necessary to derive a Mira PL and could be done entirely in the near infrared. So with our 2 anchors, we then tackled our first type 1a supernova host galaxy, which was NGC 1559. It's actually one of 4 type 1a supernova host galaxies targeted by SHOES, but this is the first one for which the data collection was completed in late 2018. And is the host of type 1a supernova 2005 DF, and it'll eventually also have a Cepheid distance. So here we obtained 10 epochs of F160, which is the equivalent of H-band, and each about 1,000 seconds with a 370-day baseline. And our sample criteria for selecting Miras in this galaxy is actually quite similar to 4258. However, we went with a slightly larger period range because this galaxy was farther, and but we had the same cut on amplitudes to ensure we were getting the same group of variables. And we added 2 more criteria, which was the surface brightness cut and something that's close to an F statistic. So the surface brightness cut was there to remove objects that were in regions of high surface brightness where we felt like we wanted to be careful because of the crowding. So as you can see here, this is our image of NGC 1559, and the Miras are in red. They're at the outer regions of the galaxy where we have lower surface brightness and small crowding corrections. And on the right, we have two examples of one Mira at the top, one object at the top that was removed due to the F statistic, and one that was kept. So this is basically just a ratio of the chi-squared fit to a sine function and a line. And then we also were very careful about tallying up the systematic and statistical uncertainties. And I just wanted to, yesterday during the panel discussion, Wendy Friedman had the summary plot for Miras and various challenges that we face in using them. And I just wanted to bring this up here while I'm discussing the systematic and statistical uncertainties, because I feel that we actually do have a pretty good grasp of many of these things that are read on here, and I just wanted to go over them. So first, the physical basis. Miras are fundamental pulsators like Cepheids, and thus they have a strong physical basis for having longer periods being correlated with higher luminosities. In addition, reddening, which is orange here, is actually what we believe is our largest systematic uncertainty. And the reason why we've budgeted 0.04 magnitudes, which is still relatively low to this, is because our observations are done entirely in the near infrared, where extinction is low to begin with. And then for metallicity, metallicity can have an effect on the Mira 0 points. However, we're not sure exactly what this is. And previous studies haven't found a definite answer on what that number is. And in fact, the 0 points of Miras found in the galactic center and the LMC have actually agreed with each other quite well, despite the very different metallicities, and same for the LMC and the SMC. So to be conservative, we budgeted 0.03 magnitudes. In addition, the number of galaxies we've calibrated with type 1As is low, but as I will get to in the next section of my presentation, we're hoping to increase that. And as I mentioned earlier, amplitude variations can happen more in the optical, but they're pretty small in the near infrared, and they also don't affect the periods. Oh, and finally, for the PL relation slope, we've used two slopes in the paper because one slope is derived from converting LMC data to from OGLE, sample of Miras, to F160, the band passes that we use in HST. And we think that some uncertainty may come when doing that. And the other is derived from the Yuan et al. Ground-based H-band PL relations. For the Yuan et al. PL relations, this was H-band, so there's also some uncertainty there. But these two actually give consistent answers when it comes to the 0 points. So we've only budgeted 0.01 magnitudes of uncertainty there. And basically, our statistical and systematic uncertainties are completely dominated by the SN1A peak magnitude uncertainty, which is 0.11 as of now. So from here, using our various combinations of anchors and also period ranges, we derived 4 different Hubble constants. And our preferred one is using the full 240 to 400 day period and using the slope derived from the LMC. And this gives us a 5.5 measurement of the Hubble constant. And these are the PLs here for NGC 1559. So as I said earlier, it's dominated by the random error from the type 1A supernova magnitude. So future work. So one thing that's really interesting is that up till now, I've only been discussing short period Miras, but short period Miras are much fainter than the long period Miras. And so there's also interest in developing long period Miras as distance indicators. The reason why we haven't done both yet is that long period Miras follow a different PL relation from the short period objects. However, their mean magnitude is 2.4 magnitudes brighter than the short period ones and 3 magnitudes brighter than the TRGB. So this is something that Wenlong Yuan is leading in exploring. And because of this increase in magnitude, long period Miras have the potential to reach volumes 27 times that of what short period Miras can reach, and 40 times or 60 times greater than what TRGB can reach. So this may even allow us to make a direct measurement of the Hubble constant. So in Wenlong's future work, CHOOSE, as I mentioned, has 4 other galaxies in which we're going to be calibrating Mira variables. And he led a cycle 28 proposal, which will obtain an additional 13 orbits to get near infrared colors for these galaxies, and also to extend the observational baseline. And in 2525, he will have years of data in which he'll be able to search for long period Miras and try to calibrate their PL relation. And I will also be, I'm also leading a cycle 28 proposal. It's an archival proposal in which we'll be searching for Miras in the SN1A field of M101. So SN 2011 FE was the nearest SN1A in decades, and everybody observed its follow-up light curves. So this data can actually be used to search for Miras because we have such a good baseline and so many epochs. And together with the CHOOSE galaxies, this will bring our total number of calibrating supernova 1A up to 6. So in summary, increasing the precision and independent measurements of the Hubble constant are needed to understand the tension. Miras are a possible independent calibrator of the type 1A supernovae that will benefit from future IR and near IR missions because we can do all of their observations in the near IR and they have good PL relations there. And long period Miras, which will have to be calibrated separately from the short period Miras, can be important for reaching even greater distances. And with our additional cycle 28 observations, we have a total of 6 local SN1A in the next couple of years. And this will bring the uncertainty in the Mira Hubble constant down from 5.5% to close to 3%. And as people have pointed out, as a former Astrobytes writer, I also feel compelled to say that if you want resources on inclusivity in astrophysics, there's a lot of good articles this week, and I've included a link here to a summary. And that concludes my talk.
Well, thank you, Caroline, for this very, very detailed talk that you gave on Mira stars. We have a few questions here. The first one is from Jeremy Mould, and he asked that would in 2015 shows PL sequences ABCD for rate variables in the LMC were C on Miras. How do you guard against contamination by the over sequences?
Sorry, can you repeat the last thing you said? I think I didn't hear it.
So there was many different PL relations for different type of variables. How do you guard against contamination by over sequences? Oh,
okay. Yeah, so that's a really great question. And we do multiple things here. Primarily what we're concerned about is trying to make our Mira sample consistent in our HST data. So we've imposed a cut both at the low amplitude and the high amplitude end. So we hope to get just that section of data, just that section of variables in that amplitude. And we also, in 40 to 58, we had a color cut because we had both J and H data. But we actually found that these color cuts didn't change. Color cuts are typically used with ground-based data in order to separate between like different spectral classes. And we found that because the HST bands are so broad, it actually didn't have a great effect on our results. So we didn't do it in 1559, but we will have colors for the galaxy for 1559 and the other SN1A hosts coming up. So we'll be able to check to see what effect this has, but we believe it shouldn't make a difference. It will be important for long period Miras, however, which is why we did want to obtain that. So the short answer is we imposed a period cut, an amplitude cut, and a color cut to try to reduce contamination from those other variables. And in simulations, we found that these were effective.
Thank you. So the next question is was asked actually by me, and is it what led you not to include the Mira star you showed in the distance to NGC 4258? So you showed this star and you say, oh, we didn't include it.
This
so
one.
I was curious about.
Yeah, the reason why we didn't include this is because it has a very large amplitude, and we found that some of the objects with very large amplitudes tend to be more heavily reddened, which is the case for sea-rich stars. And so in order to limit contamination from sea-rich stars, we put a cap on the amplitude for which stars were allowed. But here I've just shown it in the plot because it was a good example where you could actually see it varying in the images.
Okay. So the next question is by Richard Anderson, and he asked, for the LMC Miras, did you include a geometrical correction?
No, we did not include a geometrical correction for LMC Miras. So yeah, that's something we can look into doing in the future. But right now our uncertainties are so dominated by the supernova peak magnitude that we haven't examined that yet.
I think we have time for a few more questions. So the next one is an anonymous question. The person asked, does the interpreted Mira's magnitude correlate with their position in the host galaxy? This could tell us something about possible reddening biases.
So we actually didn't find a correlation. So let's see. In our sample that was left, we actually didn't find a relationship between their location in the host galaxy and their magnitude. We did look for that, but we didn't find it. So we weren't able to obtain a better estimate of extinction from there. However, like in this very high surface brightness region that we included, there was a slight relation, but we think that's more from crowding than from extinction.
Okay, so the next question is from Richard Anderson again. How do you optimize discovery of very distant Miras with period longer than a year?
Oh, sorry, with period longer than a year?
Yeah, 1 year, yes.
Yeah, so I mean, if we basically need to have the baseline of observations as long as the period of the Miras. So that's why out of these 4 galaxies, NGC 2525 was actually the best target for the long period Miras because it had also been, the supernova in this galaxy had also had follow-up observations. And for M101, it was the same. So right now what we've been doing is trying to search for galaxies which already have a baseline from other like variables that have been observed there and trying to use that to supplement what we have. Observing strategies with JWST would probably be different, so.
Okay, so one last question, because I think we have a little bit of time, and I think it's related to this previous question. Mm-hmm. Is the 10 years baseline of the Vera Rubin Observatory useful to increase the number of distance known Miras? How far can you go with that survey?
Sorry, of the Vera Rubin?
Observatory.
Yeah,
so
yeah, okay.
Useful to detect Miras, and how deep can you go?
So it will be useful to detect Miras. I think we should be able to detect Miras up to about 10 or 15 megaparsecs. I'm not totally sure about this, but I know Tarini Conchati has been like looking into it. So one issue is that we won't go deep enough to reach most type 1a supernova galaxies, but it will be deep enough to reach like, it would have been like deep enough to reach a galaxy at the distance of, I think, M101 or 4258, but not deep enough for most type 1a supernova hosts. So, but it will be useful because we will be able to discover Miras in nearby dwarf galaxies. And I think that's also pretty important as they can have a large range in metallicity. And that would allow us to examine the Mira PL in different environments.
Okay. Well, I think that was the last question I will ask you. There are still plenty of questions on Slido, and this is also valid for the 2 other speakers. I invite you to go on Slack later to maybe interact with the people who ask these questions to give them answer. So thank you again, Caroline. It was very good talk. And I would like now to move to the next speaker, please. Bruno Leingut.
I need to find my talk.
Okay. So while you set up, I will just say that you're going to talk about supernovae as standardizable candles.
Well, I should say I changed my title. So thank you very much. But I changed it to Supernovae as distance indicators. As many of you know, that is my preferred way of talking about this. And I also changed it because I will not only talk about type 1As, I want you to talk about type 2s as well, because there's some developments that are happening there. As an introduction, I'm not going to talk about the Hubble constant itself, because that's been done in various other talks, but I want you to focus on the supernovae and their use for the Hubble constant. And I thought I'd start with this here. You see here the Hubble diagram as it essentially came out of the Hubble Space Telescope Key program. This is from a review by Wendy Friedman and Barry Mador. And the point to see here is after about 100 megaparsec, this diagram is populated essentially by supernovae. There's two type 2 supernovae, the open squares here, but the rest is type 1A supernovae. And I think this is the reason that we're talking about the supernovae so much when we talk about the Hubble constant, because they are the best game in town right now to measure distances beyond 100 megaparsecs. And I should say to measure relative distances beyond the 100 megaparsecs. And I also wanted to just briefly say this is really the person behind this was Gustav Tammann, and also David Branch, among others, who really pushed this from the very beginning, long before they could know that supernovae would be doing so well. They had a great belief, I should say, but it's due to that fact that they pushed a number of people to keep on going in using type 1A supernovae for distances. I also want to add this here. I would be remiss if I wouldn't show you this diagram. This is a diagram that Stefan Taubenberger put together for the Supernova Handbook, which I think is very instructive. It shows you the magnitudes, actually the luminosity on the abscissa and on the ordinate, and on the abscissa you have delta M15 or any light curve shape parameter that you want to use. And most of those things that are plotted here are type 1A. Some of those things, some of the carbon-rich transients, we're not quite sure whether they have the same explosion mechanism or something similar to the type 1As. But if you look at this diagram, this line here is something that is often referred to as the Phillips relation or the luminosity light curve shape relation. And so you have to be able to do cosmology, you have to be able to pick out, if you want, the right supernovae, the correct supernovae. And I'll show you in a moment how that is done. Just to very brief, we think that some of those parameters that determine these luminosities in particular are nickel mass, the ejecta mass of the supernovae may play a role, possibly in some of those aspects here. There's other aspects where we're not so sure how much air influence into the physics of these explosions. So sorry about this busy slide, but I wanted to put this down because I showed you the previous diagram. In this diagram, in this slide, I wanted to show you how people go about correcting for those light curve shape factors and other factors that go into this. And so everybody, I think most people now use SALT 2. There is the color stretch method that's coming out of the Carnegie Supernova project, mostly Chris Burns. There's SIFTO, which is another one of those fitters. And there's a few more that I'm not mentioning here. And so I just have these two main ones that I show you here. So SALT 2, this is the original SALT 2 formulation. So the distance modulus is an observed magnitude, in the B band in this case, minus the absolute luminosity, absolute magnitude, plus two factors that are corrections. This is a light curve shape correction, and this is a color correction. And the way this has been treated in the past is you take the supernovae, you fit all those various parameters, and then you have these nuisance parameters, alpha and beta, and you fit those out, and essentially then we'll go back in to fit for the remaining, the distance modulus essentially here. Now, what's often done, this depends on the paper that you look at. Sometimes this is used, this is the original SALT 2, and then they have people add a separate correction for the host galaxy mass. In later papers that you see here, Skolnick et al. And Smith et al., this is now added back here. So these are the same parameters as before, but there is now a parameter that corrects for the galaxy, the host galaxy mass. And there is another parameter that corrects for biases. And it's kind of interesting for the samples that we're going to look at for the Hubble constant. These are probably not dominating, although Michael Rico will talk about this in the discussion a little later. So these are corrections that are added. Again, you fit this to existing data and then derive those. Here's the color stretch method. So here, the used magnitude in the end is the observed magnitude times a polynomial, a second degree polynomial right now, that uses this color stretch parameter. Then there's a reddening correction here, and this is the correction for the galaxy mass here again. So to do this, I think most people now use, they exclude, sorry, I should have said, so you remove outliers. So you remove the outliers that have a fast decline. So you require that x1 is somewhere between -3 and +3. The color is a regular color, so it's between -0.3 and 0.3. There is some additional parameters that have to do with the goodness of the light curve fit. How well do you hit the time of maximum, and how big is your uncertainty in the peak brightness? So you use those things to exclude objects that you think are outliers in this distribution of color, luminosity, and light curve shape. Now, in other cases, sometimes what people then do is they do a 3 sigma clipping of the data around the Hubble line. The Hubble, so everything has a Hubble residuals that have a residual that's bigger than 3 sigma, they clip that away. That's not always clear. There's not always a good physical reason to do that, I think. And so one should be a bit careful when one does that. There is lots of samples available now. These are just 2 examples. This is the one from the TRGB paper, and you see the supernova here. This is 99 objects. In red, the 18 calibrators, so 99 objects in the Hubble flow out here. And this is the foundation. They do 180 supernovae. So there's plenty of samples around to do the supernova cosmology in this way. This is all optical data for good reasons, but I also wanted to mention the infrared data. This is a paper that came out last year, Avellino et al. That's the title of the paper. Type 1a are excellent standard counts in the near infrared. And so they've gone in, they've looked at light curves. These are template light curves they construct. And they are constructed that there is 0 scatter at the peak of B maximum. So this is the peak of the B maximum, the blue light curve. And you see that the infrared light curves all peak earlier than the optical light curves. This is something that we've known for about 20 years now, actually even longer. And that was pointed out already in the original infrared papers. But if you do this, you see that the scatter around the peak here, the first peak, I should say, is tiny, is rather small. And it turns out it's nearly independent of color. It's nearly independent of light curve shape. And so you get away, by using the infrared, you get away with very few external corrections. So you don't have to fit nuisance parameters, the role of which you don't physically understand. So here, you get away with not doing this. Now, you still necessarily don't physically understand why they're all the same at peak magnitude. So this is the example. I just wanted to draw your attention to this plot over here. So this is the distribution in the Hubble residuals. Now, whenever you use Hubble residuals, you assume that you have the right cosmology. So that's actually another point that we need to think about this sometimes. But anyhow, in this case, so you take the Hubble residuals for the infrared, and you have a much better peaked distribution than you have for the optical, okay? And so in the infrared, you have fewer corrections, maybe no corrections for light curve shape, color, and host galaxy mass. And you have reduced systematics because your extinction law also is less sensitive, or you're less sensitive to the extinction at the infrared wavelength. So I think that's an important systematic point that we should keep in mind. Suhail Dhawan has done this a couple of years ago. This is using the so he looked for how many calibrator supernovae have infrared data. It was 9. And then he took all the supernovae he could find at larger distances, and that was 27. And so 9 calibrators using the Rees 2016 distance scale or Cepheid calibration, and 27, I believe, more distant supernovae gave, of course, a Hubble constant that was the same as the original Rees et al. Because it's the same calibration, but it was all done in infrared. And so with 37 supernovae, he essentially got the same scatter uncertainty with, if you want, slightly different systematics and fewer corrections and many fewer supernovae. So compared to the 200 supernovae that were in Rees et al. 2016. So as I said, fewer free parameters and decreased influence of the extinction. I have a little thing in parentheses here that I wanted to bring up. Most of you know about this, but I really wanted to sort of raise this. Oh no, this is still the infrared. No, this is about the 1As and H0. So the 1As are the connection for almost all local distance indicators. So in old language, they're the secondary distance indicator used to get into the Hubble flow. They're excellent relative distances. The Hubble residuals work. They're highly reliable and tested. I think it's true, even though you have to correct for these things. Those corrections seem to be working extremely well. And I would argue they're under control. And that's what also is shown that, and I'll show that a little later, their contribution to the uncertainty is, I think at this point, rather minimal. The H0, sorry, I didn't want to say that. So they're large and reliable samples. I would personally have some more infrared samples. Maybe the Carnegie Supernova Project has some, and there's also raising. So the absolute calibration, so the relative calibration works fantastic. The absolute calibration, essentially, you plug in what you calibrate to be the absolute luminosity, and you get the Hubble constant that your calibrator tells you it is, okay? So you use shoes, you get 74, you use the TRGB, you get 70, you use an inverse distance ladder, you get 68. The supernovae are nothing else than the yardstick. And what is important here is where you fix your yardstick, okay? And that's what it gives to you. So they're faithful translating whatever you calibrate into the absolute luminosity into the Hubble constant. Okay, and I think that's an important point. So that's a point I wanted to bring up. As I said, most of you will be fully aware of this. We hoped originally, and maybe that's just showing my age, we hoped originally that we could do this in the linear expansion regime. Okay, and so you use the pure Hubble law. Now, does it work? Because at a redshift of 0.05, the Hubble Lemaitre law, the pure Hubble Lemaitre law, and lambda CDM deviate by 4%. And so you've seen this in all the diagrams. They now use the extension. They use this extension with the Q0, the deceleration extension. And originally I thought, ooh, this is not so good, but it turns out it's actually not a problem. So at the redshift of 0.1, this is a linear relation. At the redshift of 0.1, the uncertainty is less than 1%. If you consider flat universes with omega matter somewhere between 0.23 and 0.37. So it's a very safe guess that even though you do need to correct for the cosmology, so you have to do this correction, the contribution, the uncertainty that you introduce is minimal at this point. And if you want to read the full gory details, Suhail Dhawan and his collaborators have done full simulations on this with various different models put in, and they come out with the same conclusion: it's less than % uncertainty. But we've lost that nice feature that we do not have to correct with external parameters into our measurement. And I think that's unfortunate. It's unfortunate in the sense that that means all the systematics that you now still have use to measure the acceleration, you carry sort of backwards, even though with a small factor, but you carry backwards into the Hubble measurement, Hubble constant measurement. All right, I don't have much time. I wanted to talk about type 2 cosmology, because that's, I think, is becoming interesting. There's a paper that's just out, the Jager et al. 2020, that's just appeared in monthly notices. And it's using the standardizable candle method, SCM, that has been pioneered by Mario Hamui 20 years ago, Mario. And he's been pushing his students to do this over and over again. And so it's now reaching a level where I think it's becoming very interesting. Mario and his collaborators have also developed other methods, the photospheric magnitude method and the photospheric candle method. These are mostly to use these type 2 supernovae when you don't have good spectroscopy. So the standardizable method needs spectroscopy here. So here's 2 Hubble diagrams that come out from type 2 supernovae. This is the one on the right, is the one by the Jager et al. And you see this is a fairly nice Hubble diagram, 89 objects. So this is now actually getting samples that are interesting. The scatters are slightly bigger, the residuals, it's not quite as accurate, but you can do this. This is an older version from a paper that Elisabeth Gall did in Munich. There were only a few objects here in this SCM diagram. These are mostly literature data that are included in here as well. And so to do the Hubble constant here, you do the same thing as with the type 1As. You have to calibrate, so you get a set of calibrators of type 2 supernovae that you can calibrate with the set feeds, and then you carry this out into the Hubble flow. And this paper concludes that it says, well, these may be, we may have different systematics for the translation into the Hubble flow with the type 2s, and we still get the same result, okay, as the type 1As. And I think that's a very fair statement. I wanted to go back to a method that's celebrating 40 years next year, actually 50 years next year, or in 2 years, which is the expanding photosphere method. So that goes way back. These are the equations. So you essentially measure an angular distance that's combined of a black body of the radiation that you measure from the expansion velocity and the black body, sorry, the black body flux that you have from the surface of the star. And so that has been used, but it's been hampered by this thing, this dilution factor. And so these dilution factors, there's a number of dilution factors in the literature. One is by Eastman et al. The other one is by Desar, 2005. And they've been applied to all the supernovae. Now it turns out the type 2s are all different. And so by using a simple dilution factor, you don't quite do the things right, and certainly not at the level that you need to do. So this is an example of an EPM diagram, expanding photospheres. Again, Elisabeth Gall did this. Here's a few things. There is no Hubble constant derived in this paper because it's not possible to do it. Now, I want to bring this back. So there is an expanded photosphere method reloaded. And the idea is there's other, SEAM is another acronym that's been used in it for a similar thing. And the idea is you fit every spectrum completely with a radiation transport model. And once you fit the spectrum correctly, you get two things. You get the velocity of your photosphere and you get the flux that's coming out of your photosphere, because that is what you're fitting. And so that should give you a good distance. I'll show you in a moment. Now, the one thing that we've been missing so far is accurate explosion dates. So, and that's not part of the original method. But if you have an accurate explosion date, that gives you an absolute zero in time. And that, because the slope of that function is giving you the distance, if you have the accurate zero point, that does a lot better. Now, you have to do several epochs per supernova. So here's an example. This is from a paper that Christian Vogel and collaborators published earlier this year. And these are 5 spectra fit by TARDIS, by the way he uses TARDIS. He had to actually expand it. And so this is done, and you see how accurate these fits are. They're pretty good. And when you then plot this up, so in addition to having the uncertainty here in the zero point, and you have these points here, then you get actually fairly good distances. So this is 2000. So this is what I described before. So this is the fit to 2005 CS, which has a TRGB distance and planetary nebulae luminosity function. And this is the best fit that he finds for this one supernova in that galaxy. Yes, I'm done. This is a first set that he has put into his thesis. He doesn't allow me to show you what Hubble constant he gets. It's also clear it's very difficult because we're not really in Hubble flow out here yet. So there's not enough data to really do this. But I wanted to raise this. So there's a program that we've started to fix this problem. So we're going to use the expanded photosphere method according to Christian Vogel. He's of course part of the program, to about 30 type 2 supernovae in a redshift range that hasn't been covered yet, 0.03 to 0.1, completely independent of the distance ladder. And so we have a program, we do 6 epochs spectroscopy and photometry per supernova. So that gives us enough data to get the distances. And so we got 8 objects in the first semester, currently on hold for obvious reasons. And we can add, so part of those 30 supernovae are actually coming out of the supernova factory. So that's the end. I think 1As are reliable secondary distance indicators. I think we fully control what's happening. This is also the reason that I'm the only person who really talks about the supernovae, because I don't think it's really debated what's happening here. I do think it would be nice to get to the infrared, the near infrared, because we have fewer dependencies there. It's harder to observe, I understand, but I think we get the tools. So I'm a little worried that by adding, by the fact that we need to take acceleration, deceleration, acceleration into account in the fit, that we add uncertainty that may become relevant for the 1% goal that we're all aiming for. As I said, type 2s are promising, and the EPM, I think we'll see how that's going to work, because that doesn't know about Cepheids or anything else in the distance ladder. That's a one-shot distance to these supernovae. And so we'll see where that leads us. Thank you.
So thank you, Bruno. Thank you for this very optimistic talk, I would say, because we have a lot of perspective about keep using supernovae to even increase the accuracy of H0. So we have quite a few questions. So I will go at them already. So the first one is from Benan Javan Mardi from Paris Observatory. And he asks, the nuisance parameters, alpha, beta, etc., are fitted simultaneously with the cosmological model parameters. Can this be an issue for direct measurement of H0?
Well, it's not an issue at this moment, although I should say, every time you fit a nuisance parameter, you're trying to get rid of, well, you may have an issue with systematics. If for whatever reason that nuisance parameter has a distribution that you don't quite understand, and that's the physical problem, then you're prone to systematics. I know many people will now say, well, we have so many supernovae that we can just fit this out, so we can make it a statistical problem. And I think that's correct. But there's a little bit of a worry. I think for what we're doing right now, the supernovae are fine. Once you're going to push below 1%, you have to look at this again. But that certainly could be a source of systematic problems.
Okay, so the second question I think is related to that, is asked by Richard Anderson, and he would like to know, given the complexity of the supernova zoo, how concerned are you about non-vanilla type 1A contamination affecting the mapping of the Hubble flow?
Right, so I was concerned for my whole career, more or less. And I have to say, I'm coming around, and I think people are doing this right. They're doing these selections of the light curve shapes. That's what I tried to show. All these selections are, from what we understand from the physics, are the right thing to do. We do think that some of those outliers may be different physics, different explosions, whatever. So I think I'm actually as you said, more optimistic than I used to be, but I think we've made a big step in the right direction. So I'm not as worried as I was most of my life.
Okay, maybe one last question, because before we move to the panel, and maybe the panelists can start turning on their videos while I ask the question, is what are the prospects to increase the number of observed supernovae 1A in the infrared domain in the coming years? And this is asked by Pierre Carvela.
Right, so there's a program, I mentioned it briefly, RACENS, and I'm sure somebody online is part of RACENS. They've been collecting infrared data for quite a few years. The one paper that they've written is this Avellino et al. Paper, where they clearly indicate what they want to use the infrared for. But I'm not aware that they've published the paper. I'm happy to be corrected if somebody knows more about this. So there is a program that has been doing this for a few years, and so some of that data is already there. The SCP, as far as I know, has done a lot of infrared work, and so they probably have quite a bit of data that's coming along. I'm pretty sure that several programs are on the way to do this. And we don't need that many. We don't need the hundreds for the infrared.
Okay, thank you, Bruno. I think we need to move to the panel discussion. So for this discussion today, we have the 4 speakers of today. So Leonard, Grzegorz, Caroline, and Bruno. And we'll be joined by Pierre Carvela, Dan Skolnik, Richard de Vries, Michael Rigaud, and Marina Rechkuba. So I would like you all to turn on your video. And I will leave the microphone to Marina, because I think she's the one who's going to animate this discussion.
Okay, thank you very much, Anton. Thanks a lot to the conference organizers, and especially thanks to the speakers for motivating this discussion and for bringing a lot of interesting topics. So my name is Marina Rechkuba, and I have put together the discussion topics from my fellow panelists, who are Pierre Carvela, Dan Skolnik, Richard de Vries, Michael Rigaud, and well, myself. And I will share now a presentation. So let's see. Just a moment.
We still don't see it.
Yeah, no, should come now. I was a bit trying to make sure that I don't show two wrong windows. Can you see it?
Yes, we can see it. Yeah.
Okay, very good. So today, for the discussion, we have collected a number of different topics, ideas that were bounced among the panelists, and also with speakers who were contributing with some topics. So I will keep this slide here, and then when we go into a specific discussion that was brought up, for example, on the sample biases that were brought up by Bruno, by Michael, by Dan, we have some slides or on the comparison between the accuracy that we can get from the parallaxes from Gaia or period luminosity relations. We have some slides. So we'll try to do it this way in order to really make sure that we have as much as possible discussion among people. So the very first item for the discussion that was brought forward was to look at what are the connecting topics for the presentations from this session, and how the different techniques complement each other. And I think there was also one of the questions that I noticed just now from that was not yet voted high enough that went to Bruno, that actually I think connects this. How do we bring really the best sample of supernovae that should be used, and how do we make sure that different distance indicators that calibrate this best sample of supernova, or rather galaxies where this supernova exploded, to make sure that we really compare in as similar way and to remove the selection from the supernova biases that you also mentioned are coming in.
So you want me to answer this? There's so many projects on the way that do this. So we have a number of large surveys that have done local supernovae. I mentioned the Carnegie Supernova Project. There is the CFA project. There were these papers by Hicken et al., where Adam was involved. There is the Foundation project now. So there's 3 data sets, and there's a recent paper where now people put the data from a single telescope together to make sure that they have as few systematics. They don't have to transfer magnitudes from one set into another, et cetera, et cetera. And so the data set is all there. I think we have, in the optical, we have, what, a couple hundred good supernovae. The fact that everybody uses the JLA is another one of those examples. So the data, I think, is there. I don't think there is much work that's needed to do the selection, and that is done through these light curve parameters. And so people need to explain why they use these selections, and they do this in their papers. And then I think we're there. I don't think we have to worry too much about connecting nearby supernovae to distant supernovae. There is, once there is 43 shoes calibrators, you're going to be hard pressed to say, oh, these are all one part of the distribution or something like this. So I think we will know in a couple of years how much sample differences we have, but I don't think that's going to be a big issue.
Okay, what about, Richard also mentioned on the chat, on the Slido, what are the 2 most important issues to solve for improving the precision and accuracy of supernova distances?
If Adam is online, I mean, I don't think the supernovae are the major contributor to the uncertainties.
Well, I think Michaela and I are going to have a slide on that.
Yes.
Okay. Shall I then?
Sure, because I think it's connected to both questions, actually. I would slightly disagree with Bruno and maybe also with Dan about how much is important as a selection function. I think there is something that is illustrated here in this slide on the top left, which is there is a key step that we are doing here that is concerning us for the type 1 supernovae part, is we have to assume that the average humidity of the swings in the Cepheid host sample are the same as the one in the Hubble flow sample. This is the key of what we are doing. And there is, I think, the core issue. There are many things that we have checked that are working very well, and I think Dan will go through that after that. But one of the things here is that there is, by definition, a different way of selecting the sample we are looking at. One has to have Cepheids, the other one has to be in the Hubble flow. So this is trivial to say, but it's not. It may have some consequences, and one of them that I've raised in some former analysis is that we know now for several years, for almost 10 years, that supernovae vary as a function of their environment, either because they are some high mass hosts, just hosts, or young environments. And for instance, I think it might be an effect that Cepheid hosts favor young environment. And the amplitude of the difference between supernovae from young and old environment, depending on who is looking at it, might vary from by a factor of 3 from 0.05 to 0.15. So 0.15 is what I think we have, and many more other people have found something much smaller. And so if the effect is as high as I think it could be, the effect on H0 could be 3%, which is a lot, which is really, really high. So obviously, a lot of other people think it's much smaller. And what is surprising is what I highlight here is that when in the shoes analysis, they have done the trick of trying to mimic this Cepheid selection function, which is really non-trivial. So by doing that, they look either at only using star-forming hosts from the Hubble flow or only using late-type galaxies from the Hubble flow. Then they find that basically H0 is not changing. So if H0 is not changing, it's either because there is no magnitude difference between young and old, or that the Cepheid hosts are not so much favoring young environments. So I think, so Dan will continue on that, but I think this question of how the supernovae are connected to their environments and how this is connected to the selection function, I think this is, in my opinion, one of the key systematic from the supernovae side, at least. If not the only systematic left to look at, and I think it's not closed issue, but so yeah. So Dan, maybe you want to comment on that?
Yeah, sure. So right, so in for the shoes analysis, right? So as we show on this slide, we are now taking only supernovae late type galaxies, and we think if we measure the effect that's in our sample, and we do kind of the correct demographics measurement, where we say kind of how many supernovae are it could be affected by this systematic, we estimate that the impact is on the level of like 0.2 in H0. So it's a combination of kind of what we're showing here, that the step that we see is significantly smaller than what Mikhail sees, and it's also the kind of the demographics of getting the same kinds of supernovae in the second rung and the third rung can be relatively similar. So that makes us less sensitive. So this is as we say, this is a systematic that the community has spent a lot of time on, and I think more work still needs to be done, but we've made a lot of progress. Just want to highlight a number of the other things that we've worked on, which are other systematics. So this has been mentioned by Bruno, which is that there's a recent paper by Dewan et al. With a number of the SHUS members, where we now can do a full covariance matrix propagation. I think Lloyd asked a question in the chat of, can we connect Pantheon to SHUS? And this paper kind of establishes that framework, and I'd say kind of the next SHUS paper will have that. It'll basically be a big Pantheon plus SHUS type thing. Adam talked a bit about looking at peculiar velocities and voids. We don't see using supernova data any strong evidence for a significant void that could affect the H0 discussion. And the effect of peculiar velocity treatment seems to be small. We kind of have a homogeneous calibration across surveys. And one thing that's come up is how sensitive we are to a cosmological model in our methodology. So I think Bruno mentioned that we might have some sensitivity, and this has now been looked at really nicely in Broud et al. 2019. We find that sensitivity is very small. So measuring any of the nuisance parameters, the way we do it now, we don't carry that through. Then kind of redshift uncertainties, this has come up in the literature a lot over the last couple of years. So what we've looked at, we found that this is also relatively small, and Tamara Davis will give a talk about that tomorrow. And then we're still kind of working on various standardization techniques. This is kind of like this paper by Brout and myself, which tries to explain a lot of kind of what these various host effects are due to dust, and we feel like we could capture a lot of the effect. We estimate kind of with our explanation that the impact on H0 is at the 0.5 level. So I'd say all these things do affect H0, but they don't seem to kind of rise up beyond half a percent or so from what we see from the data.
Okay, any other comments from other panelists on this topic? Then, Richard, do you want to say something? Or, no, okay. Then another item that was brought forward, I think Gregor mentioned it, the importance of obtaining absolute distances to Cepheids, tip of the Regine branch, Miras in different environments. I think in part, this could address this the dependency on stellar population effects, corrections for metallicity, corrections for maybe also reddenings. but and maybe it could also help with the question that was just brought just a moment ago by Michael about older or younger populations having slightly different supernovae as well. However, I have a bit of a hard time seeing that we have so many galaxies where we can probe that. It will take time. Any further? I mean, there are a number of galaxies where I think we can still mine the data that already exist for Cepheids, tip of the red giant branch Miras, but they were not collected with the specific focus. And this was one of the items that was discussed yesterday, the difference between collecting data from the literature versus very focused and clean samples.
Just maybe, Marina?
Yes, please.
I just wanted to make a brief comment on that point of the environment. I think it's something really important. I've seen that we rely a lot at the moment on the LMC as an anchor for many different types of stars, in particular the Miras that we have seen with Caroline's talk, but also of Cepheids. So we have a very good distance to the LMC, which is very nice, but it's not a grand design spiral galaxy like the one that are used in the distant universe, the host of supernovae. So I think in the coming years, I'm expecting that we will see a return of the Milky Way as an anchor, because with the improvement of Gaia accuracy, we will have a better grasp on the galactic Cepheids and also galactic other types of stellar standard candles. So I think it may have a very nice advantage that it will simplify again, I would say, the distance scale and reduce the number of rungs to reach the Hubble constant in the end. I think this was the original goal of the SHOES project, to have a more direct, more simple approach of the Hubble constant. And I think with Gaia, we have probably a way to go even a little bit farther in terms of simplification of this distance scale.
Oh, yeah, I think that's a great point. I also wanted to mention that for the Mira distances, we primarily use actually NGC 4850 as an anchor, and we've incorporated the LMC in the most recent. But the NGC 4850 is a large spiral, so we hope that some of those effects will be canceled out. And we also saw that the relative distance between the LMC and 4858 is actually consistent with what we would have expected from the Miras. So we think, I do think it's really important to look at different environments, and Gaia will be great if we can get those parallaxes for Miras. But at the moment, we don't see a large effect from that in our own data.
And if I may highlight something here, whether or not the effect I'm talking about is true, I think it's a bit dangerous that we try to basically using the TRGB or the Miras to check the Cepheids distances. If we do that only for the Cepheid hosts and not for all the other where we could do this analysis, and if by any chance there is an issue with how this Cepheid host has been selected, then we will continue to have this problem and we won't understand where it's coming from. So I think as much as possible for tools that can go everywhere, like the TRGB, they should just try to go for volume limited measurements and disregard all the other selection function, because I think this is host and selection function, as we just said with Dan, is one of the main issues, I think. So for all the techniques that can do volume limited, please do it.
Actually, if I can add a comment here regarding the use of the Milky Way as an anchor. If you look at the literature, and we did this a couple of years ago, we did a meta-analysis of all distances to the galactic center ever determined, well, since a century ago. The distance resulting from young populations and from old populations is actually different by 0.2 kiloparsecs to the galactic center. So we still don't actually understand the local calibration. So I always wonder how that feeds into, more distant supernova calibrations, because we need to understand the local calibration. And that leads me to the common answer. Let's use Gaia, because Gaia will solve all problems. But this is actually one of the issues I brought up for this discussion. If you look at Gaia distances, right, the parallax uncertainties will increase progressively at greater and greater distances. And so you get radial anisotropies in the distance distribution of various objects. And Marina, if you can go to one of those slides that actually shows that, the next slide. Yeah, this is from the poster from data release 2. You see radial streaks here, while period luminosity relations to Cepheids in particular can be obtained at least to groups of objects at between 4 and 8% accuracy. It's been shown in the last couple of years. So at what point do we not trust Gaia anymore? And at what point become period luminosity relations complementary to Gaia? And perhaps that's a question I should ask Leonard.
Okay. Well, it's clear that since the parallax distance has error in parallax, which increases for fainter magnitudes, and that also means more distant objects that also have smaller parallaxes, then the relative error in distance increases very quickly with distance. And that is why a trigonometric parallax is only useful for determining, for example, the period luminosity relation for objects where the parallax is really significant, better than 5% or so. And that is already the case for maybe a handful of Cepheids or so. But it will certainly improve very rapidly, because if we half the errors in parallax, we reach twice the distance, which will include many more of these objects. So I think already in the next release, the number of useful calibrators like Cepheids will increase by a big factor, and even more in coming releases. But I don't have any numbers directly in my head, so I can't be very precise here. But you are, of course, right that as we go further out, they are no longer useful, at least individually.
Leonard, you were mentioning that the next release will have, or rather Gaia DR3 full release, will have also M31. So which depth?
Yeah, well, what we will release in this Gaia Andromeda photometric survey are just the photometric light curves for all the sources in that cone. So of course there will also be parallaxes and so on, but not as time series, of course. Yeah.
What about crowding at that distance, Leonard?
Yes, there are lots of problems with crowding, but you should also remember that Gaia has a angular resolution of 0.1 arcsecond, which is much better than most or all ground-based surveys up to date. So for example, we can distinguish individual objects, for example, in Andromeda or LMC, much better than with many typical ground-based surveys. The resolution is comparable to HST.
If I may add a small point on the question of Cepheids in the galaxy with Gaia, I think there are several hundred Cepheids that will have parallaxes better than 1% with Gaia soon, probably in the DR3 already. And if the problem of the 0 point of Gaia is mastered, is resolved, then this would enable an extremely accurate calibration of the period luminosity relation, assuming that we can master also the reddening, because the parallax is not the only question in the calibration of the PL relation. But if we have a very good 3D map of the reddening, like that is promised by the Gaia survey, this should give a remarkably accurate calibration of the period luminosity relation, and that also where the infrared data, and particularly the K-band, are really very, very important, because this will decrease the sensitivity to the reddening and therefore allow for a really, I mean, rock solid calibration of the PL relation of cepheids in a normal metallicity environment, I mean, which is the Milky Way.
Can I follow up and ask, so can Gaia be used to help calibrate TRGB? We talk a lot about Cepheids.
I think Jeremy, if he's connected, he could comment on that. He actually wrote a paper last year, I think. For at least so far, I think the problem was that it was not yet accurate enough, because many of these tip of the red giant branch stars were quite bright.
And the answer is yes, I can jump in. And we had a program as part of the Carnegie Chicago Hubble program to monitor giants using a robotic telescope at Los Campanas just for that purpose. So yes, it will be extremely useful. Sorry, this is Wendy Friedman.
Sure.
If I may comment on
Thank
that.
Yes, please.
Yeah, so I think it's not possible to calibrate tip of red giant branch in just one environment. For example, in the Large Magellanic Cloud, we have a range of colors for the tip of red giant branch, and we need to include color in the calibration. So, for example, you can do the calibration based on several SS Wendy and Barry did, and my group too. You know, you need a couple of observations. For example, tip of a giant branch in the Large and Small Magellanic Cloud, plus, well, hopefully in the Milky Way and in some globular clusters. But it would be very difficult to calibrate this technique just based on one environment.
Agreed.
Yes.
This is Rachel, really quick. I'm working in Sloan. We have a survey where we'll have metallicities and stellar parameters for giants, where we may gain some insight onto color and metallicity from the Milky Way.
Okay. I wanted to bring up one more thing. Let me see. What do I have here? The presentation. We had one more point about extinction reddening laws. Here, I have seen that the Schlegel maps were mentioned. There were recent tests of the Schlegel maps with SDSS, and I have seen in the literature a lot of people are using these corrected maps or recalibrated values from SDSS. And I'm not really, you know, an expert on SDSS, and one of the things that scared me here when reading those papers is that this recalibration is of the order of 14%, and there is also some difference that was observed between the northern and northern and southern hemisphere, which at some point was also discussed as possibly due to inaccuracies in the calibration of SDSS itself, or whether it is really in the maps, in the dust maps there, and due to the temperature calibration. And then we have, when using Gaia, we have to take care also to transfer from the Gaia to the whatever color or photometric system that we are using. I think this is going to improve, continue improving, and this is going well. But then there are statements that are brought forward, like going to infrared helps. And yes, it helps, but there is, and certainly helps a lot actually, but there are also variations in infrared. And here I'm just bringing one example that comes from the use of the galactic bulge red clumps, where the red clump, I'm not sure if you can really see my mouse, but the red clump in the bulge, because of the very, very large extinction, is really a slanted line, which then in the 4 panels on the right, the area is subdivided into 4 regions, and each of these regions has a different value of the AKS over EJ minus K. So these variations to exist. Okay, galactic bulge is the maybe extreme environment, but how do we know that when we go towards external galaxies, towards star-forming regions, or even towards higher redshift universe when using supernova, how are these corrections incorporated? And here I'm talking about not only the corrections in the foreground reddening, but also internal to the galaxies. Any takers? I mean, Caroline, for example, for the Miras, you said that you have been looking at areas that are outside of the star-forming regions. Miras themselves are in the tip of the red giant branch where you start having dust around Miras as well. This is why the carbon-rich Miras actually have this PL relation, which tilts and is much broader. It's not really that well defined. How is the, have you found any evidences that using different areas in your galaxies would have slightly different width of the PL relations, which would also indicate scatter due to dust? So
I don't think we have found this in 1559 or in 4258, but if you do look at the LMC, I don't know if you, I might have some background noise. If you look at the LMC and you look at the larger, the longer period Miras, which we haven't been using, that are also carbon rich and happen to be in the bar, I think they have a different scatter and different PL relation. And so that's one reason why we have been limiting ourselves to short period oxygen rich Miras, because they tend to be much cleaner. They have less dust, and they're also located in cleaner regions too with less reddening. But you can see this effect, I think, in the LMC when you look, but not so far in 4058 or 1559.
Okay. Any other comment? I think we are starting, we reached our time, so I got the message from the organizers that we should start wrapping up. If there are no further urgent comments, I would really like to thank all the speakers and all the panelists. This was really great. Thanks. And we can continue discussing on Slack.
Yeah, exactly. Thank you, Marina, for animating this discussion. I think, like yesterday, I would like everybody for the last few minutes that if you can turn on your camera so we can all see each other's face, and take a few minutes to thank you all for participating today, all the speakers, all the panelists, and everybody who asked questions on Slido, or everybody is participating right now on Slack, and you can go on. I mean, there is no time limitation for this. And we would like to invite you to come back tomorrow for our third day. Same time, there's also on Zoom or on YouTube. And so, yes, see you tomorrow.
Thank
Bye,
you.
everybody.
Bye-bye.
Bye-bye.
Bye.
Bye.
Bye, everyone.
Bye, thanks.
And